Virtual Day 13, March 31st. All right, we're starting with the second part of rational functions. Remember, like we talked about yesterday, rational functions is just division of polynomials. And remember the definition of polynomials has to have rational exponents and real coefficients. So here are the steps that we're going to do when we're starting with the graphing, and then we're going to look at how to write the function from the graph, and then we'll look at. So the first one, I'm just going to follow through these steps so you can reference those. The first one, we have x minus 1 over x squared minus 4. I usually start with lowest terms because it helps to define your domain. This is squared. We have x minus 1 over x plus 2 times x minus 2. Remember, your domain restrictions occur where your denominator equals 0. So for step 1, my domain is going to be where x plus 2 equals 0 and x minus 2 equals 0. So our domain has restrictions x such that x cannot be equal to plus or minus 2. 2 is lowest term, so that's where if anything cancels out, I always leave it in factor form. So this right here, nothing cancels out. That's our step 2. X-intercepts, that's where your numerator equals 0. Your numerator equals 0 is going to give you where it touches the x-axis. So x minus 1 equals 0. So your x-intercept at 1. Your y-intercept, that is the ratio of your constants in your simplified form, not simplified form, in your original form here, standard. So ratio of constants. So we have a constant y equals -1 over -4, which is 1/4. You could also look at that as where x equals 0. That's kind of where that comes from. For symmetry, I'm going to show you how to test for symmetry on this one, but in the future you can just look at it in your calculator and no need to test for it every single time. Actually, I'm just going to go ahead and show you on your calculator. The testing for symmetry is on the key on the outline. I'm trying to make this quick for you. I'm just going to type my original into my calculator. Make sure you put your numerator in parentheses and your denominator. You're welcome to use Desmos, but again, the parentheses will help you with typing. Look at my graph. So you're looking for symmetry with respect to the x-axis, y-axis, or the origin. This one doesn't have y-axis, does not have x-axis, but it does have origin symmetry. Step 5 is our vertical asymptotes. Your vertical asymptotes occur where your denominator equals 0. So those are our domain restrictions as long as it didn't cancel out. So we have vertical asymptotes at x equals plus or minus 2. 6 are horizontal asymptotes, like what we talked about yesterday. Whether it's proper, improper, or neither. The degree of the numerator here is 1. The degree of the denominator here is 2. We have a linear over a quadratic. That's where those degrees come from. So 1 is less than 2, so this is a proper fraction, which means that we have a horizontal asymptote at y equals 0. So anytime it's proper, remember that y equals 0 is your asymptote. You don't have to do any math there. Then we're going to sketch the graph. Also look at your calculator here. If your asymptotes are of odd multiplicity, which means it has an odd power, the first power to the third power to the fifth power, then your end behavior is going to go in opposite directions at the asymptote. If it is even multiplicity, then it's going to go in the same direction. So our x-intercept, we have an x-intercept at 1. and a y-intercept at 1/4, so that right there. Our vertical asymptotes at ±2. And our horizontal asymptote, because it's proper, is at y=0, so that one's kind of hard to grasp, but this one I'm showing you is the least that I expect to see. So on the left-hand side, our graph looks like this. I don't need exact points through there. As long as all of this is exact, I'm good to go. And then in the middle, this is what's going on. And then on the right, something like that. Feel free to write down your questions and send them to me in an email if you have them. And pause at any time if you need more time to write. We're going to continue. Step 1 is my domain. My domain here cannot be simplified. Nothing happens there. We just have that domain restriction where our denominator equals 0. It's x such that x cannot be equal to 0 because my denominator is just x. My numerator is difference of squares again. So my lowest term x plus 1, x minus 1 over x. Nothing cancels out, so that is lowest terms. Step 3 are your intercepts, so x-intercepts from where your numerator equals 0. So we have x equals plus and minus 1 there. You're going to set each one equal to 0 individually and solve using the zero property. Your y-intercept is the ratio of your constants. So my constants are 1 on top, and this would have x plus 0 there. Over 0, you cannot divide by 0, so there are no y-intercepts. Number 4, your symmetry. I'll type this right in the calculator. And it looks like this one also has origin symmetry. Number 5, your vertical asymptotes happen where your denominator equals 0, your simplified denominator. Number 6, horizontal asymptotes. My degree of my numerator here is 2. That's a quadratic polynomial on top. And my degree of my denominator is 1. That one is linear. We have x to the first power. So since 2 is greater than 1, this is improper. Which means it's going to have an oblique asymptote. To get the oblique asymptote, I'm going to go here and do this. We're going to need to do the long division. So I'm going to have my x on the outside, my x squared plus 1 on the inside. Don't forget to put the placeholder there for the missing terms. So x times what gives me x squared? Write it like this and simplify it. I'm left with x. X times x is x squared. Subtract there. Those cancel. 0 minus 0x minus 1. X 0x, that would be plus 0. So you have an oblique asymptote that y equals x. Now check that. I usually put that asymptote in under y2 and make sure that my graph is actually approaching that, and you can see how closely those are together. You can see this one's getting closer and closer to the line y equals x, and so is this side. So then I'm going to graph everything that we've got. My x-intercept, there is no y-intercept. My vertical asymptote is at x equals 0. So that will be at my y-axis. Well, there's no y-intercept. I'm going to have an oblique asymptote at y equals x. So that it would go here, here. I'm just going to sketch that. So we have a 45-degree angle. And then there's my graph. And on to number 3. I always go factor first, especially with something like this. It helps with your domain. So my numerator has a GCF of 3x. If I take out that 3x, then I'm left with x minus 1. My denominator, the leading coefficient is 1, so I can list my factors of my constant. Factors of 12, that could add or subtract, give me 1 or 4. To get positive 1, I need positive 4 and negative 3. I have x plus 4 and x minus 3. Nothing cancels out, so this would be my lowest terms. Step 1, my domain. Remember, that's where your denominator equals 0. So it's going to be x, such that x cannot equal negative 4 and positive 3. Oops. Sorry. This would be step 2, my lowest terms, or simplified form. Step 3, your x-intercepts. X-intercepts where your numerator equals 0. So you would have 3x equals 0 and x minus 1 equals 0. So that means if you divide by 3 here, a lot of people get confused and they want to say that x equals 3 as well, but remember you have to divide by 3. 0 divided by 3 is still 0. Equals 0 and 1. My y-intercepts, ratio of my constants. So my constant on the numerator, there's not a constant, so that'd be like a plus 0. So you have 0 over negative 12. 0 divided by anything except for 0 is just 0. For my symmetry, looking at my symmetry, you have 2x squared minus 3x, and x squared plus x minus 12. Make sure you put your numerator and denominator in parentheses. This one does not have any symmetry. Number 5, my vertical asymptotes. For your denominator, your simplified denominator is 0, so I have there that x equals negative 4 and positive 3. 6, my horizontal asymptotes. My degree of my numerator is 2. This is a squared function over a squared function. So the degree of my numerator is 2. Degree of my denominator is 2. 2 equals 2, so this is a neither proper nor improper. That means that I have a horizontal asymptote at y equals the ratio of my leading coefficients. So that's y equals my leading coefficient on top is 3. My leading coefficient on the bottom there is 1. So I have a horizontal asymptote at y equals 3. Looking at the graph on my calculator and using the things we just found, I'm going to graph this. I have an x-intercept at 0 and at 1. I have a vertical asymptote at negative 4 and at positive 3. And then I have that horizontal asymptote at y. And then on the left, it's going to go like this. On the right, like this. And then in the middle, it's going down. It's not a perfect parabola. You can tell by looking at your graph. And then those are good. Both on the left and right going to approach that y equals 3. Okay. one more like that, and then we're going to look at writing one from the graph. My domain, so I'm going to go ahead and write this in simplified form first. My numerator, my leading coefficient is 2, and this is a quadratic. I can't take out a GCF, so I need to use the box to factor. Remember to use the box. You put your first term in the top left corner and your constant in the bottom right. Multiply those two together. 2 times 2 is 4. And I need factors of 4 that will add my b term, which is negative 5. The factors of 4 are 1 and 4, or 2 and 2. To get negative 5, I need negative 4 and negative 1. This part, it doesn't matter which box either one of these goes into, you'll get the same thing either way. Then you pull out your GCF in each row and column. So here we have a x, and here we're going to have a negative 2. You always take the sign that's closest to where you write it. Here I have a 2x, and here all I have is a 1, but the negative is closer. So that's what that's going to look like. So my lowest term and my denominator there is difference of squares. I'll simplify that. I'm going to have 2x minus 1 over x minus 2. And my denominator, x squared minus 4, is x plus 2 times x minus 2. My x minus 2's cancel out. So where that cancels out, that's going to create a hole. It is still a domain restriction, but it is not a vertical asymptote. So first I'm going to list my domain restrictions. X such that x is not equal to positive or negative 2. My lowest terms is written without whatever is canceled out. So we just have 2x minus 1 over x plus 2. You're going to use your lowest terms for your x-intercept and also for your vertical asymptote. Number 3, your intercepts. My x-intercept is going to be where 2x minus 1 equals 0, 2x equals 1, x equals 1/2 when you solve that. Your y-intercept, you can use either your original or your lowest terms. Either one will work here. It's still going to be the ratio of your constants. That's why y equals negative 1/2. If you did your original, you'd have 2 over negative 4, which would also give you that negative 1/2. Your symmetry, you always want to type your original. If you type in what's simplified, it'll look the same, except for it will not give you the whole. Divided by x squared minus 4. Make sure you put your numerator and your denominator both in parentheses. This one has no symmetry. And then step 5, my vertical asymptotes, excuse me. Now you only want to use simplest form. Sorry, can't spell today. Simplest form. So I only want the denominator in my lowest terms or my simplest form. So x plus 2 equals 0. So that means I have a vertical asymptote. X equals negative 2. Now, because this canceled out, I'm also going to have a hole at where the term canceled out. So x minus 2 equals 0. I have a hole at x equals 2. Step 6, my horizontal asymptote. This one is neither because my degree of my numerator is 2. My degree of my denominator is 2. My degrees are equivalent, so this is neither, which means I have a horizontal asymptote at y equals the ratio of the leading coefficients, either 1 or 2. And then I'm graphing. Oops. Your graphing calculator will not show you the whole. I don't remember if Desmos does or not. Way to check for your whole is to look at your table. Your whole happens at an error. At your vertical asymptote, you should also have that error. So that is kind of how you fix it. I have x equals 1/2, so if that's 1, there's that x-intercept. Now y equals negative 1/2, there's that. I have vertical asymptote at -2. And I have a horizontal asymptote at 2. I always wait and do my whole last when it fits in. My whole is at +2, so on the left hand side, my graph looks like this. And on the right hand side, my graph is going to go like this. And when I get to where my graph would be at x equals 2, I'm just going to put a hole there. And that's what that should look like. So writing the function from the graph is probably the trickiest part of today. Remember that you have the rational function is equal to p of x over q of x, both of which are polynomials. So I'm going to talk about these in two separate situations. I'm going to talk about the numerator first, which is q of x. So your x-intercepts are your numerator, or your numerator equals 0. That's that of x, or p of x. I have an x-intercept here at -2 and here at 5. So I have x equals -2. The multiplicity there is 2 because it just touches the x-axis. And I also have x equals 5. That one has a multiplicity of 1 because it crosses through. So because of this, my numerator could be, so this is one option, right? X plus 2 squared and x minus 5. This is one option. My denominator, or q of x, depends on my vertical asymptotes. So I have a vertical asymptote at x equals, if you look here, I have one at -5. And then I have another one at +2. Now, we need to talk about the multiplicity of this. So the multiplicity of the one at -5, because it's going in opposite directions, is going to be multiplicity 1. So my denominator is going to have x plus 5. This one is an odd multiplicity because in behavior is going in opposite directions. Now at 2, this in behavior is going in the same direction, so this one's going to have an even multiplicity. When it's odd, we're going to assume 1. When it's even multiplicity, we're going to assume it's squared. And that's because the in behavior is going in the same direction. So my denominator, q of x, could be, this is one option, my x plus 5, because it's an odd multiplicity, it would be to the first power, or just x plus 5. And then my x minus 2, even multiplicity, would be to the second power. Then we just need to talk about our horizontal asymptote. If you look at this one, it looks like it's approaching 2. So I have a horizontal asymptote at y equals 2. So when your horizontal asymptote is at 0, it's proper, which means the degree of your numerator is less than the degree of your denominator. If it's a linear, an oblique asymptote, so it's going like this or like this, then that means it is improper, which means the degree of your numerator is greater than the degree of your denominator. If it's just constant, then that means that your degrees are equivalent. So my degrees of denominator and numerator are equal. And 2 is the ratio of the leading coefficients. So what I've got here, the degree of my numerator here is I have x squared times x cubed. So this is degree 3. My degree of my denominator, I have x times x squared, which is x cubed, so it's degree 3. My degrees are already equivalent, so I don't have any imaginary zeros to worry about. This is the ratio of my leading coefficient, so that means I'm going to have 2 over 1 to go with that. So one option for this function would be 2 times my p of x plus 2 squared times x minus 5, over 1 times my q of x, which is x plus 5, x minus 2 squared. And then the last thing we're going to look at is an application problem. Reynolds Metal Company manufactures aluminum cans in the shape of a cylinder with a capacity of 500 cubic centimeters, half a liter. The top and bottom of the can are made of a special aluminum alloy that costs 5 cents per square centimeter, and the sides of the can are made of steel that costs 0.2 cents per square centimeter. Express the cost of the material of the can as a function of the radius of the can. Alright, so the capacity here, that is my volume. And then the sides of the can, top and bottom, are 5 cents per square centimeter, and the sides of the can are 0.2 cents per square centimeter. So I'm going to start by drawing the net of the can. The net is what would happen if you cut it flat. The sides of the can would look like a rectangle. And you're also going to have the top of the can and the bottom of the can. And we want cost as a function of the radius. So I'm going to talk about my volume, and I'm going to then talk about my surface area. So my volume, it said, was 500 centimeters cubed, or cubic centimeters. The formula for volume of a cylinder is pi r squared h. Area of the circle times the height. So this is going to be my height here. This right here is my circumference, which is the same as this here. The circumference equals 2 pi r. So what I can do is I can set this up, this 500, in terms of my pi r squared h. So 500 equals pi r squared h. And what I want to do is I want to get this in terms of h, so that I can plug it into my equation for h and have only r as the variable. So what I want to do is solve this for h. I'm going to solve this out for pi r squared. You get h equals 500 over pi r squared. So that's how I got rid of one of the variables. I'm just solving that for h using the volume that's given to me. I need to find the surface area, which means I need to find the area of each piece here. The area of a circle is pi r squared, and the area of a rectangle is length times width. So the area of the rectangle is going to be, if I know that my length here is my circumference of the circle, because that's going to go all the way around my circle, then my length would be pi r, and then my times my width is my height. So that means that my area of my tops, so the area of the top and bottom, is going to be, because there are 2 of them, 2 pi r squared. The area of the sides is going to be 2 pi r h. So now when I'm talking about cost, this 0.05 and the 0.02 are go in here, and the total cost of the can is going to be the sum of those. So the cost of the top and bottom is cost of top and bottom is going to be that 0.05 times the area. The cost of my size is going to be that 0.02 times by 2 pi RH. Now the only other thing I'm going to do is substitute for that 8 so that I have it in terms of one variable, and I'm going to add these guys together. And my cost, I'm going to distribute that 0.05 times 2, 1, so I have 0.1 times pi r squared plus 0.2 times 2 is 0.04 times pi r, and then my 500 pi r over pi r squared. Simplifying this a little bit here, this is the same thing as over 1 when you multiply fractions, multiply straight across. You can cross reduce there. My pi's cancel, my r's almost cancel. I'm left with 1 on the bottom, and then 0.04 times 500 is 50. So I have 0.1 pi r squared plus 20 over r. To write this as one rational fraction, I'm going to multiply this by r over r. So I have 0.1 pi r cubed plus 20 over r. So all I did there was just a common denominator. This is my equation in terms of my cost, in terms of my can, the radius of my can. We are going to graph the function on our calculator. So I'm just plugging this in by 0.1 times pi x cubed divided by my x. X is my r in this equation. Now I need to see this positive side. The reason I'm not looking at the negative side is because I'm not going to have it negative. Surface area of volume cost. I'm not going to have anything like that. I'm going to adjust my window, and it looks like I want my window to probably stay from 0 to 10 on my x side. Just 15 just to make sure. But my y minimum is still up there around 8, so I'm going to make my maximum go for 65 and see if we have a good picture there. That looks good. It says to graph the function, and then what value of your r or for your radius will result in the least cost. So at this point, we just want to find our minimum value. Or you can't see that. Our minimum value. So on my calculator, I'm going to find that minimum point, second trace, option 3. Move my cursor to the left of that minimum. Hit there. To the right of my minimum. Hit enter twice. And then my radius that will give me the least cost is 3.176. That 9 rounds that 6 up to a 7. And then what is the least cost? That's my y value. And that's going to be about 9.47 cents per can. All right. Let me know if you have any questions from this. Please make sure you're keeping up with your homework and have a great day.